It's an honor to have an opportunity to give another one of these social networks and health training workshop lectures. In this lecture, I would like to go back to some of the material from the lecture that in the notebook that we went through in the introduction to community detection section that we recorded in 2019 and provide some updates that I hope will help you be a better user of the community detection tools that are already available in R now in 2021, and also think a little bit about what's going to be available hopefully in the very near future. So the two parts of this lecture on community detection really are about what's available now and what we, and some theory about what we hope will be available in the near future. The first part covers the first three items on this list. First, we're going to assume that you remember at least some of the material from the 2019 lecture, or you've been exposed to ideas about community detection in networks, and in particular, the modularity perspective on community detection. We're then going to use some bleeding edge materials in the iGraph package available in R. There's a new cluster Leiden function that will allow us to do a lot of things that were at the end of that 2019 discussion, where we were trying to use resolution parameters, but now we don't have to work so hard to get the software to work inside of R. The new version of iGraph is going to have a cluster Leiden in it that completely native to R lets you manipulate the resolution parameter. And we'll close out this first part of the lecture with some pointers to some other software that it would probably be useful for you to be aware of. Maybe we'll cover those in a future social networks and health workshop another year. In the second part of the lecture, we're then going to go take a look at what we hope will be available for doing community detection in R in the not too distant future. Some more advanced methods for identifying resolution parameters, and in the context of multi-layer modularity for picking the interlayer coupling parameters, built on the so-called CHAMP method, which we did talk about back in 2019, but we'll briefly summarize some of that. And that will then lead us into some more recent work by others, identifying an equivalence between maximizing modularity and stochastic block model inference. And that will together provide a new method that leverages these two different ideas to create a so-called finite state map on the CHAMP set. The second part of the lecture all involves some methods that are available in Python, and again, that we hope will be available in R in the not too distant future. Again, as always, with a talk that I give about community detection, it's an enormous field. I will admit that my perspective is very biased, and that you're getting the picture of community detection in networks through the lens of my own experience and my own intuition. It's a huge area. I'm going to try to point you to some good review articles, but we're really covering just a small part of the literature here. Hopefully we're covering a useful part of the methodology that's available to you so that you can be a better user of some of the community detection tools that are available in R. Here are some pointers to some of these reviews. I think I've pointed out some of these in the previous lecture. The one at the bottom I want to highlight. It was a preprint the last time we gave a lecture in this training workshop. It's since appeared in the Oxford Handbook of Social Networks. If you're coming at community detection from an application perspective, thinking of this as a tool that you want to use, I'm biased because I'm a co-author on that paper at the bottom, along with a bunch of former group members, Sarai Shea, Natalie Stanley, Clara Grinnell, and Dane Taylor. But I really think we endeavored in that paper at the bottom, case studies in network community detection, to take a perspective not just of how do you do community detection, but why you should do community detection, and when might it be useful for you in different application settings. So as a very quick review on the modularity perspective of community detection in networks, we go back to remind you what the modularity quality function is. So it's going to be a quantity Q, which is something you can measure for each partition, here denoted sigma. A partition is a hard partitioning of nodes into communities. That is, every node gets one and only one community label in this non-overlapping community framework. The modularity quality function Q here is built up out of your adjacency matrix. So this is the presence, absence of the edge, possible weight of the edge from I to J. Some null model with Pij, which captures the expected edge weight. Now, in the context of undirected networks, which is where we're going to do most of our work today, because it's what's available inside the cluster Leiden package inside of iGraph. This is typically going to be one of two things. It's either going to be the product of node degrees. So here Ki is the node degree, or in the case of a weighted network, the node strength of node I. Similarly, Kj is of node J. And then 2m is in the undirected network. It's the sum of all the degrees across all nodes. That is, m is the total edge weight in your network. In the modularity framework, this is typically for an undirected network, this product Ki Kj over 2m. In the so-called constant Potts model, which we'll see in the notebook when we get to it, we just treat this as a constant. So this gamma then, that's inside the modularity matrix, serves as a resolution parameter that multiplies the Pij. And finally, the delta piece is just an indicator on the nodes I and J, whether or not those two nodes are in the same community or not. So the total quality here is a sum only over node pairs that are within the same community. And the optimization problem to identify your communities is to find the partition sigma of the nodes into communities that maximizes the quality Q. And again, I mentioned the resolution parameter. This resolution parameter is going to be really the most central piece of what we talk about today. This resolution parameter indirectly controls the number and sizes of the communities, because if you see its contribution here in the formula, if I make gamma very small, then there is very little penalty for me to put two nodes together in the same community, even if they're not connected to each other. This will promote that I will have a smaller number of larger communities. In contrast, if I make gamma very big, then I don't want to put I and J together in the same community unless the edge weight, Aij, is enough to overcome the contribution here. And so a large gamma is going to give me a larger number of then much smaller communities. And this is going to be the most central piece of our discussion today, is exploring the space of possible resolution parameters and deciding what values of the resolution parameter are reasonable for our application, for our data at hand. I do want to mention very quickly that, again, Pij can take a number of different forms. In the so-called constant Potts model, it's really just a constant. And so if it's a constant value, we don't even need the gamma, because that's just another constant. So here it's just a p, some constant value p, which you might interpret in an Erdős-Rényi sense as the probability of any node pair being connected. Again, for undirected networks, the most common form of modularity is this product of Ki and Kj here. Just I've changed notation on you, sorry. Divided it out by 2w instead of 2m. The intended meaning is the same. And again, it gets multiplied by a resolution parameter gamma. We're not going to talk at all today about directed or bipartite networks. There are also null models for signed networks. And it's just important to know that those things exist. Only in some of the clustering, the community detection functions inside of iGraph do you have any ability to do anything beyond the constant, so-called constant Potts model that is the Erdős-Rényi form here, and the regular modularity form of Newman and Girvan. But it's important to know that those exist. So again, as I've already said, the biggest focus of today to hopefully help you be a good user of these tools is that we're going to focus on modifying the resolution parameter inside of R. Now, the last time we talked about this at this training workshop in 2019, unless you're a good Python user, we really were standing on our heads trying to get people's systems capable of handling the functions that were available at the time, because there was this beautiful package that Tom Kelly had put together that used reticulate to call Python from within R in order to access some of these so-called Leiden algorithm tools that were available in Python. Luckily, Vincent Trog, one of the creators of the Leiden package, has recently been working to bring at least a part of the Leiden package to the iGraph that is available inside of R. And the cluster Leiden function, which we'll use heavily today, will be in the next version of iGraph, which will be version 1.2.7. As of today, when I'm recording this in May 2021, I believe the current version of iGraph is 1.2.6. And in order for us to use this in our notebook today, we actually have to go to the development branch of iGraph in order to have access to this function. Don't worry, it's not that scary. I was able to do this on a new laptop that I happen to have. So I know that it's not only working because of a bunch of legacy things that I happen to have installed. All I needed to do was install the remotes package. I needed to make sure I had some tools available to my R, and then I could use the remotes package to install directly from the GitHub with the command here. Now, if you, I'm showing you here this page straight from the R iGraph GitHub. If you're on Windows, you need to make sure you have these so-called R tools installed. If you are on a Mac, you have to do something different. If you're on Linux, you probably have the whole thing already set up to do everything from source, so it should be okay. If you're on Windows, you need this RTools 40 to be installed on your machine. If you're on a Mac, you need to follow the instructions here to make sure that you have both Xcode and GNU Fortran 8.2. But literally that was it. Beyond just a base R and RStudio installation that I had done, all I needed was Xcode, GNU Fortran, as labeled here. I needed the remotes package, and then it was a simple matter of installing the development branch straight from GitHub with this command at the R command line. And at that point, if you check what package of iGraph you have, hopefully what it tells you is that you are running something at least version 1.2.6 and higher than 9.1.1.8. Again, none of this development branch work should need to be done in the near future. As soon as they go to version 1.2.7, it will just be a regular CRAN install of a package like you install any other package. It'll just be in the default iGraph and you won't have to worry about that. Okay, so with that, that's the setup. And now what I'd like to do is I'd like to jump into our notebook. Now, you can find, I'm not going to talk everything through in the notebook. You'll see I'm a little bit verbose in the notebook, but what I would like to do is I would like to be able to show you how some of this worked in practice on some example networks so that you can hopefully do similar kinds of things with your data that you are interested in. So again, everything here is running on the development branch of iGraph. There's a lot of notes at the top of this document, again, about how that got installed, and a number of references that have been very important to my thinking about how to do network analysis in our the new edition of the book by Kalakshik and Shardy, I think is particularly excellent. And again, referencing a lot of the community detection review articles for you here. So we dive in. And the nice part here is that a lot of this, once you've got cluster Leiden, is no more difficult than running any of the other cluster routines that you are presumably already have already seen and might even be very familiar with in running within iGraph. they're great routines. I'm a big fan of a lot of them, but the problem has really been up until this point that there has not been an easy way to efficiently explore the resolution parameter space. It actually turns out that, as someone helpfully pointed out to me since the last lecture, that the cluster spin glass routine does have a resolution parameter in it. And that I had overlooked in my previous discussion about whether or not there was any way to do this natively within R. It is there, you can use it. My experience is that the spin glass routine is not very efficient and not compared to many of these other tools, particularly on large networks. It tends to take a long time and not come up with optimizations that have modularities or qualities as high as some of the other routines. But it is there and is something you should explore if you have a small enough network and you want to use that to explore the resolution parameter space. But now that cluster Leiden is going to be available, really, I think it's just amazing how fast it runs. Again, if you got everything installed correctly, you should be able to actually look at the help for cluster Leiden. If you cannot look at the help for cluster Leiden, that is a dead giveaway that you do not have a recent enough version of iGraph installed on your machine. So now what we're going to do is we're going to go to just one of the most beloved and most overused examples of all time, the so-called Zachary Karate Club. We talked about this at the last lecture. It comes up as a very common example network in network science and in particular in community detection. And I love this quote from Eric Kalakshik that if your method doesn't work on this network, then go home. And so we're gonna start there because we're actually going to see that there's going to be a situation by the end of the second part of this lecture where we have to be careful about whether or not our method works on this network or not. For the purposes of using cluster Leiden, you can see that all we need to do is pull down the data. We print some notes about the data here for ourselves. I'm not going to go looking through all of this. There's this standard force-directed layout that gets generated. And so you might just be tempted to go with the default of generating community assignments by just sending the karate data straight into cluster Leiden. And that already seems to do something a little strange. The important thing to understand here, and the reason why we're starting with just the default, is to make sure that you see that the default in cluster Leiden is it uses this so-called constant Potts model, where it's the adjacency matrix minus a constant. And what you're controlling then when you change the resolution parameters, you'll be changing the constant that you're subtracting off. There are perfectly, the constant Potts model is a perfectly good alternative to the usual modularity where for an undirected network, it's a product of Ki, Kj over, normalized by the total edge weight. It's going to have a different behavior because it's a different formula. So it's going to solve a slightly different optimization problem. In a lot of ways, it's no different than when we do normal unsupervised clustering of data, right? We have many different tools and they have different properties and they yield different kinds of clusters. Well, the constant Potts model and the modularity framework provide different kinds of communities. One's not necessarily better than the other. They have different settings in which they're useful. I just tend to use modularity in a lot of my own work. And so I'm biased that way. And we're going to spend a lot of time on that today. But I wanted to start with the fact that the default is the constant Potts model here so that you can see that if you just use it out of the box, you might not like the answer you get. And that's actually by design. If you page through some of the discussion that Vincent Trog has had about setting this up within our iGraph, he's definitely appears to my reading of what he's written in some places. He wants to nudge the users to be very aware of the fact that there is a resolution parameter here. You might be tempted to think, oh, I'll just go with the default and avoid the choice of a resolution parameter. But avoiding the choice is just a different kind of choice. And I think Trog is very pointedly here by just leaving the default resolution parameter for one, even for the constant Potts model, he's nudging the user to be aware that they might and that they very well want to change the resolution parameter. So if we just leave it in here on the Karate Club data, we get 16 communities. Most of them are singletons. Some of the others are small. We can look at the membership of it. We can look up which member of the Karate Club is in which of these 16 communities. It might be more helpful to just plot the force-directed layout here. Now you can decide whether or not you like these communities. This is not the level of community detection that we're usually interested in with the Karate Club, right? The story of the Karate Club is that they have a disagreement and they split into two rival clubs, and we want to see how that split relates to the social relationships within the club. This isn't a split into two groups, this is a split into 16 groups. So what's going on here? Well, the data is weighted. And you're going to see me do this a lot. I'm just going to save this for later in case I want it. So I'm just going to call it KCCPM1, constant Potts model at a resolution value of 1. What's going on here in the constant Potts model is the value that you typically want to be thinking about subtracting off, so that you want to set to your resolution parameter. If it's an unweighted network, you want to be thinking about subtracting off values that are near or on the scale of the density of the graph. If you're in a weighted network, this Karate data in this case happens to be weighted, you want the weighted version of that density. So we just pull out a few quick statistics here of our Karate network that we have. The graph density is just a little bit under 14%, we see. We can, of course, compute that ourselves if we just look at the total number of edges and we divide by n choose 2, where n is the number of vertices. So we can recapitulate that the density here is just under 14%. The weighted version of this is to sum all of the edge weights and divide by n choose 2. And we see that that weighted average, if the way to think about that is the average weight between any pair of nodes, whether or not they're connected, that average weight is a little over 0.4. So when we subtracted off the default resolution parameter of 1, that was a number, well higher than this. And so the average IJ element of the corresponding matrix being summed in the constant Potts model was negative. And so we ended up with many small communities. If we instead plug in this same weighted average of the weight between any pair of nodes, we actually only get 10 communities. A lot of them are still singletons. So you could decide whether or not you like that output or not, but we're definitely getting a bunch of singletons and then seeing some slightly larger communities. We can look at the membership of that if you want, and we can see what the plot of that looks like. And this is starting to at least look a little closer to the typical Karate Club story, particularly if we think about a lot of these singletons here, or these ones that are right on the border between these two large communities. It looks like there's a split that goes through the middle here somewhere. And then we can argue about whether some of these nodes should be on one side of the split or the other. As one more use of these memberships, you'll see that through a lot of the lecture here today, I'm going to strongly advocate that the power of contingency tables. It's really tempting if you want to compare two labels, whether it's a ground truth label and some communities that you came up with, or in this case, I want to compare two different partitions that I came up with, the communities that were found by the constant Potts model at the default resolution of 1, and the communities I've now just obtained at the weighted density. When you want to compare these two things, it's often very tempting to want to go to a single score, and I'm not above doing that. That's I do it all the time. We go to normalized mutual information or adjusted mutual information, lots of scores like this. We're not going to do a lot of that. Actually, I don't think we're going to use those scores in this notebook here today. What we're going to do instead is we're going to, in most cases, have a small enough number of communities that it's just easiest to just directly look at a contingency table of how many nodes in our network were in one of the 16 communities, in each of the 16 communities in the one partition of community labels onto the nodes, and then in the 10 communities in the second partition that we had. So, right, we can see here that all 6 nodes that were previously in community 1 in the CPM1 labels appear in community 1 in the CPM density labels, but that those CPM density community labels, that first community also includes the singleton that used to be community 7, the singleton that used to be community 11, and the singleton that used to be community 13, right? This is how you read these tables, and we're going to see a few more of them along the way here. But you're really just counting the number of instances that had the label in the one partition versus what label did it have in the other partition. Before we leave the constant POTS model behind and switch over to modularity for the rest of the day, I think per this nudge that Vincent Trog is giving the user, I think it's instructive to see what happens if we switch over to the unweighted version of the Karate Club network. So we're going to delete the edge attribute of weight here, and now we have the unweighted version of the Karate Club. Or again, if you are thinking about it, all the edge weights now are just 1, right? It's a binary 0, 1. Is it absent or present? And so now when we run cluster Leiden at the defaults, remembering that the default is to use CPM, and the default is going to be to use a resolution parameter of 1, it doesn't partition the nodes, it doesn't group them together into clusters at all. It says every single node is its own community. And that's not terribly useful, but it's also completely what you should have expected under this scenario. The value of 1 being subtracted off in the constant POTS model is going to zero out the value of 1 of every single edge that is present in the system. So there's the way that the algorithm runs, and that it starts initially from every node being its own community and starts merging them together and then moving them around between the communities. There's no good reason for it to merge any 2 nodes into a community here, because the penalty being subtracted off is exactly the same as the value of putting 2 connected nodes together. And again, this is a feature, not a bug. This is a nudge by the author, Vincent Trog, to tell you that you really need to be using resolution parameters. So, and again, it's not a terribly instructive plot when every node is its own community. So now we're going to go on and we're going to switch to doing this with modularity. So when we do this, again, I'm very verbose here for the reader who wants to go back to this notebook and follow the references. And again, you can see the previous lecture from 2019 where we managed to do something kind of like a resolution parameter native to R by instead using this trick of self loops that was proposed by Arenas, Fernandez, and Gomez. We're not going to use the self loops today. We're going to use the traditional resolution parameter that gamma that was on the slides that I showed before, because we now have the capability of doing that inside the cluster Leiden package. And then in the second part of the lecture at the end of this notebook today, when I talk a little bit more about some of the theoretical methods that I hope will be coming to R in the future, we're going to go over some of these references here about CHAMP, about relating modularity maximization and stochastic block models and connecting it to this new modularity pruning package that Ryan Gibson has available in Python that we hope to be making available in R in the not too distant future. So now this is going to be the kind of framework you're going to see us do a lot. I like to, as I say in this notebook in many places, I like to give the data an opportunity to try to tell me what is the correct scale at which I should be identifying or resolving communities. To me, it's like my first car, I'm old enough, my first car had an AM radio only, right? And you would tune the analog dial and you would sort of you would get fuzz and static, and then there'd be a signal. And the signal would exist for a little while as you tuned the knob and tried to find the center of it, and then you'd lose it again. Maybe partially analogous to that, what we're going to do is the knob we're going to tune is the value of the resolution parameter, this gamma, in the modularity formula. And so here we're just going to wrap in a for loop a range of gamma values in small steps going from 0.25 to 2 in this example. And we're going to build up this plot. We're going to call cluster Leiden. We're going to send it the karate data. We're going to use the modularity objective function. We did change here. I'm just going to point this out the one time. You'll see this in other calls, in other for loops later in the document. One of the parameters is the number of iterations within the Leiden framework to try to improve the communities that are identified. The default is 2. It runs super fast, so I changed it to 3. You can try larger or smaller values. It didn't seem to need more iterations than 3, but occasionally 3 did enough better than 2 that I decided to leave it here. And we're going to change the resolution parameter. And there's a lot of different things that you can do with the output from this to try to identify the differences in the communities that you find at different values of gamma. The simplest thing that I'm going to do here in this notebook is I'm just going to, for each value of gamma, I'm going to compute the number of communities that I have at that value of gamma. And then that's what we're going to plot, is the number of communities that we have versus gamma for the different data sets that we're going to explore today. And so you see for the Zachary Karate Club, if you have gamma small enough, you get 2 communities. And then at some point you get above a value of gamma and it seems to jump to 3. And then it eventually jumps to 4. And then it eventually jumps to 5. And beyond this, it sort of goes away quickly. And as you make gamma large enough, eventually you get up to just every node is its own community and you have 34 communities. But the way I read this plot, even without having any other information in it here about whether or not, for instance, the 4 community partitions that I'm obtaining over this whole region, whether or not they're actually exactly the same 4 community partition or not, this is a clue to me, right? That I have a nice big plateau at 2, arguably also a nice plateau at 3 and at 4 and at 5. Really, any of these values from this plot, 2, 3, 4, or 5, communities seems to be a reasonable number to me. And so then the next way that I would normally approach this, if I didn't know anything about this data set, is I would start comparing what do I get at 2 communities and 3 communities and 4 communities and 5 communities. And of course, this network is small enough that we can also just plot what does it look like. So we have something that would at least seem to be very close to the expected split, the so-called factions in this data set, into the 2 groups. In fact, right, we can just look at the table of the actual faction assignments and the memberships in this 2 community split, and it's a perfect agreement in this case with the factions. All 16 nodes that are labeled faction 1 are in the community 1. All 18 nodes that are in faction 2 end up in community 2 here. What happens then when we go to 3 communities and to 4 communities and to 5 communities? Well, 3 communities looks a lot like 2 did up above, but now there's this little piece that separates off. And we can see that here in the picture, but we can also see that directly in the corresponding contingency table. If we compare the memberships in the 2 community split to the 3 community split, you can see precisely that the old community 1 in the 2 community split just splits to become 2 communities now in the 3 community split. And similarly, when we split into 4, when we're picking in each subsequent run here a resolution parameter that's in the middle of those plateaus that we saw when we ran over gamma, when we swept over gamma, looks like it just breaks off another sub-community. And sure enough, when we compare the 3 community and the 4 community split, we can see a split of the old community 3 into 2 communities. Something a little more interesting happens when we go to the 5 community split. Something weird starts to happen in the middle, and you can see this in the contingency table, comparing 4 communities to 5 communities, that it's not as clean as the story we were telling before. So if you know, this is obviously not a complete evaluation of the karate club, but it hopefully at least demonstrates to you the kinds of thinking that I would encourage you to use using the resolution parameter now that it's so easy to do so with the cluster Leiden function. This all becomes even more useful, even if my spelling isn't perfect. This all becomes even more useful when you go to larger networks, because it tends to be the case that for larger networks, the default resolution of modularity at gamma equals 1, particularly in large sparse networks, tends to have communities that are too big in many cases than the ones that you might be interested in for your application. I just pull up the Enron data set here because it's one of the ones that's built in and easy to study. Unfortunately, the current implementation of cluster Leiden only works for undirected graphs. So we're going to make that change here. We're going to recast it as an undirected graph. Importantly, we can see that we saved under this option. We've now saved every one of the edges. So we now have a multi-graph. We have 125,000 edges between these 184 nodes, each one of them representing an email that was passed from the one user to the other user, and we are now ignoring the direction. Again, just like before, we're going to wrap this in a for loop. We've changed the values of gamma slightly for the case that's at hand here, but we're going to run cluster Leiden like we did before, and we're going to generate another figure of the number of communities that we observe versus gamma. You can see this is a lot noisier than the karate club was. It's a lot noisier than the other examples we're going to look at in the notebook. Looking ahead, you'll see that it's maybe not much noisier than some of the things that we see in some other applications that CHAMP and that this new pruning method that I'll talk about are capable of handling. But you know, just eyeballing this, if you were looking at this, you know, maybe this is signal that there's something on the scale of 14 communities here. Maybe this is signal. Maybe this is signal up here. I'm just going to grab a community assignment somewhere roughly in the middle of this plateau and another one somewhere roughly in the middle of this plateau, and just compare them. So we're going to do a gamma of 2.2 and 3.2. And again, that doesn't give us so many communities that we can't at least look at a comparison between the two of them at the level of a contingency table. You can take a look at this and you can see that community 6 pretty much stays the same, community 7 stays the same, community 8 stays the same. Situations like that are indicative to you of there are some very robust structures, community affiliations inside this data set, and it might lead you to investigate more about who the members are in some of those different communities and use this as a tool. Ultimately, again, community detection is really only a tool, right? It's a way of clustering your network data, and you want to now use the communities that you find. Hopefully you're getting robust structures like this that you find. They aren't just sensitive to one run of an algorithm or to very small changes in your resolution parameter. You want to identify the robust structures, and then you can go study them to find out more and use it as a tool to understand your data. As another example to really, I think, hammer home, I hope, the need to go beyond just the default resolution here. I love this example. This is an old example that goes back to a paper by Michelle Gervin and Mark Newman. This is the set of college football teams who played each other in the fall 2000 season back when this used to be called Div 1A. I've copied the GML file from Mark's webpage over into my directory here. You can also obtain it from his webpage here. read graph reads the format right in. There's 115 teams. There are 613 games between those 115 teams, so every game is an edge. We're not worried here about who won the game or who lost the game, just did they play. Importantly, this 115 teams is only Div 1A, and then occasionally, if you know anything about college football, what used to be called Div 1A is now really FBS. They play games against what used to be called Div 1 AA, which is now FCS. And so this is not all college football games, but it's sort of what people often think of as the top tier of college football at that season. And this data set's interesting because, well, it's interesting for many reasons. I've had a lot of fun with this data set over the years. The vertex attributes that we see, right, there's an ID attribute, a label attribute, and a value attribute. And importantly, the value attribute here is a numerical code for the conferences in college football. So, and you can read more about that in the text file from Mark's webpage that accompanies this data set. If we look at the labels, that will be the university names of all of the nodes here that have a value 0, then it spits out these 9 schools, including the one that I currently teach at and the one affiliated with this workshop. This is the old 9-team Atlantic Coast Conference that exists in 2000. If you pick out the value 3, you get these 12 schools back from when there were actually only 12 schools in the Big 12 conference. I'm a little snarky here about the fact that the Big 12 now has 10 and the Big 10 has either 14 or 16, depending on how you count. If you don't follow college sports, don't worry about any of this, it doesn't matter. So now for the purposes of what does matter here is these conferences represent agreements between schools to play each other. Within each university plays a majority of its games within its conference, with the exception of a few independent schools in this 115 universities in this data. So if you just go compute at the default resolution parameter, which I'm gonna put in explicitly here, but putting resolution parameter of 1 would be the same thing as putting no resolution parameter in at all. What do I get out? Well, it looks like I get out, and I'm going to plot now the communities of the network, and I'm going to use this value that corresponds to labeling each node by this conference indicator. So the 9 schools in the ACC are these zeros over here that have been grouped into a community. But you can see that there's a lot of mixing of some of the numbers. And you can see that even better than in this dense graph, sort of dense plot. You can see this if you look, again, surprise, at a table of the 12 different values, 0 to 11, that are assigned to each of the vertices, and the 10 communities that are identified by cluster Leiden for modularity at the default resolution. And you can see a lot of agreement here. I mean, this is pretty good, right? All of the ACC is in community 2. That corresponded to the picture that we had up above. But you can see that some of the other communities, community 1 is an interesting little mix of things that were in value 7, value 10, a couple others. You can see the community 7 over here is also split between values 9, 10, and 11. There's definite agreement with the communities and the conferences, but it's maybe not perfect. And full disclosure, it shouldn't be perfect, because one of these labels is just schools that are independent, and there are other relationships here between some of the schools that are not being captured by this value attribute. But nevertheless, it raises the question of, was this default right or not? And so let's go back and generate another one of these for loops like we've been doing before. And so I'm just going to change the values again. Having experimented with the data set, then this is my knob, that I'm going to turn and see how many communities do I get as I vary gamma. And you can see that the value of gamma here at 1 seems to pop out. And that would presumably be our 10 community solution that we're getting right there. That's not much of a signal in terms of me thinking about robust performance of the algorithm as I change gamma by just little bits. The number of communities rises quickly as I increase gamma, and then maybe it settles down a little bit at 10, a little bit at 11, and then bang, there is a big range where you get 12 communities. And importantly, that range is not straddling the default value of gamma equals 1. This is a blindingly obvious, almost screaming out of the data signal to me that I want to be looking at resolution parameters over here, not a resolution parameter over here. Yes, that default resolution parameter had a lot of nice features to it, but it was not a robust identification of a partition of nodes into communities like I'll expect over here. Granted, I have no guarantee in the picture as I'm drawing it right now that these 12 community solutions are the same 12 communities. Indeed, there's probably little differences between them, but this is probably where I want to be working. And we'll see more about this data set and its performance under CHAMP later on. So when we plot now our 12 communities, which I'll label FC12 here, that I get at a resolution parameter of 2.5, you can see up to some of the, running out of colors choices here that, again, there's very strong alignment with the communities. But it's definitely doing some weird things in some different places that are different than what we had before. So it's, this is one solution and you want to be looking at multiple solutions. If we look at, again, our tables that we love looking at, right? We again see that the ACC that we highlighted before is a community unto itself. What we're starting to have is a slightly different organization of some of the communities down here that one could, I believe, argue makes slightly more sense than the default values that we had up above. In particular, we can compare what did we have up above, the 10 community solution we had above, with the 12 community solution we have now. And you can see where it's split out a few different things. One of the things that is interesting here is the new community 10. Looks like it pulled 1 out of the old 6 and 4 out of the old 7. You can see here that the old community 1 is now been split into 2 different communities, which are labeled 1 and 6 now. And if we go look at some of those communities, so like we go ask, well, what are these 6 nodes right here? These 6 nodes appear to be what was the old Big West Conference, if you study the history of college football, and it pulls it out here as a separate community, which is particularly interesting because these are 6 schools that had a history of playing together. But at the time of the creation of this data set, corresponding to the 2000 season, right, they aren't being given the same the same conference value. So I think that's really interesting. All right, one last example to sort of talk about how you can study these things that I'd like to look at. Favorite examples of mine that you'll see come up some more in our discussions are congressional roll call similarity networks. So these are weighted, dense networks between members of Congress who are being assigned a weighted edge corresponding to the fraction of roll call votes for which those 2 members of Congress voted the same way within a 2-year Congress period. And so the 2 examples that I'm going to look at here are both from the United States Senate for the 85th Congress, which is basically January 1957 to the very beginning of January 1959, and the 110th Senate, which is January 2007 to the first few days of January 2009. So we'll just sort of round and call that 2007 and 2008. These are two very different periods in American congressional history. The 85th Congress is at the beginning of the era of civil rights legislation. The 110th Congress is a hyper-polarized, my team versus your team kind of setting. Let's just take a look very quickly at how looking at communities of these senators based on how they vote compare with each other. So I've saved the adjacency matrices that for these roll call similarity networks. The definition of these adjacency matrices can be found in this old 2009 preprint by Andrew Waugh and others, including myself. We're going to read in these adjacency matrices directly, and then we're going to look at the senators that are in it, and let's just plot what the roll call similarity network looks like. And so this is for the 110th Senate, which I told you is a hyperpolarized situation. But these are weighted dense networks. In this specification of the roll call similarity network, two senators are still connected to each other, but with an exceptionally small weight. Even if they disagreed 99% of the time, there's 1% of the time that they agreed with each other, and so they're getting a 0.01 edge. You can argue that that's maybe not a really great way to have defined the network here. Certainly for the purposes of this force-directed layout, it does not capture the polarization of the Senate that exists at that time. You can maybe see that, it's a slightly elongated hairball, and maybe it's a little more interesting if we look for clusters. Here I'm just going to use the old cluster Louvain method, which is running only at a resolution of gamma equals 1. It's going to give me a modularity a little over 0.18. You might be thinking that doesn't seem like a very high modularity value. Again, it's all about context. What is high and what is low for modularity depends on the kind of network, the density of the network that you're dealing with. In this case, perfect separation of votes into one team and another team, you can work out on the back of an envelope, would have corresponded to a modularity of 0.5. So 0.18 is a healthy way along to the run of 0.5. That would literally be if Team Red and Team Blue never had a vote in common with each other. That modularity in this case would be 0.5. Of course, there's a little bit of overlap. 0.18 is not the highest modularity in the history of the Senate, but it's a pretty high one. It is higher than average. If we now plot those communities, you can see that now the colors are indicating to you, they're helping your eye identify that the pattern that there is polarization in this data. And I talk some more about whether or not 0.18 is high or not. I also encourage you to go look at Andrew Waugh's paper to see some of the historical comparisons. Now we're going to see, well, do we get the same thing from the new cluster Leiden function at the default resolution if we use the modularity objective function? And you can see from the table here that we get precisely the same split into two communities of the 110th Senate. So now we can ask who are in these two communities. Well, if we check the membership, right, it's just a bunch of 1s and 2s. More interesting is to look at the names, because the way that this vote view data that we're using here is labeled, every one of the senators is identified by the state they represent, and they have a party label right out here that this being starting with a 2 indicates that this is a Republican. When we get later to some data that you can't see yet, but you can't see yet because this is all one community, you can see every one of these starts with a 2. This is a community made up entirely of Republicans. And if we look at the membership of community 2, now you can see that all those 2s became 1s, except a couple interesting cases. Olympia Snow from Maine was a Republican who often voted with the Democrats. Of course, Bernie Sanders is not a card-carrying Democrat. And so he's labeled differently here. His declared party affiliation is different. But you can see that basically it has just split right on the nominal party affiliations of Republicans and Democrats. So by way of contrast, we now do the same thing for the 85th Senate. And we pull the data in. These commands all look exactly the same. We're just pulling the 85th Senate now instead of the 110th Senate. The hairball, you can ask, well, I don't know, does the hairball have quite the elongated shape that it had before? Maybe if we try to identify some clusters, we can see. So now if we go use cluster Louvain, we can see that the modularity that comes out of it is only 0.09. So the level of polarization, if you're thinking of modularity as a measure of polarization, and there's good reason to think so, you can go back to that paper by Andrew Watt, the level of polarization is only half in the 85th Senate of what it is in the 110th Senate data. Of course, as soon as we color the nodes by those community labels, you can kind of see the shape and the pull and the tension on the network there. If we now go look at the memberships, we can see here a community that is mostly Democrats with a few Republicans. Again, the 1s and the 2s, so there's a couple Republicans in here. If we look at the membership of the other community, you can see it is almost all Republicans, occasional Democrat, another occasional Democrat. So, but it still seems to be very much a split into Republicans and Democrats. Interestingly now, if we run Leiden at the default resolution, it finds 3 communities instead of 2 at a gamma value of 1. Remembering that we couldn't change gamma in cluster Louvain. We can only do so inside the cluster Leiden function. And this is interesting, right? Because it looks like it's pulled 13 of the members of what was community 1, which you remember was mostly Democrats, into its own community. And it's pulled 3 members of community 2, what was community 2, which was mostly Republicans. So who's in this third community? If you know anything about the civil rights era of legislation and the history of civil rights in the United States, this answer does not surprise you to find a community that is largely made up of Democrats representing southern states, along with throw in a couple Republicans into this mix. And so now the question is, well, should there be 2 communities or should there be 3 communities in this data? Should is an interesting word, and it's why I deliberately put it in quotes. Let's go do the same tuning the knob that we've done on the other data sets up above. Let's sweep gamma over a range. It is a much tighter range now than it was up above because we get very different kinds of responses from changing the knob here on this dense weighted graph than what we were getting on large, sparse, in most cases, unweighted graphs up above. But there's still the presence of these plateaus that I think are indicative of interesting levels of investigating this data. I mean, of course, the plateau, if you make gamma small enough, every node goes into one community together. That's not an interesting result. There's a large range of gamma here where we find 2 communities, a smaller range of gamma where we find 3. It could be interesting to see, this is a range of gamma where we find 5. Is that, I haven't looked closely at that plateau. It's possible that that's just one partition into 5 communities. It's possible there are multiple 5 community partitions up there. But this kind of analysis, this sweeping of the resolution parameters, this giving the data the opportunity to tell you what's the meaningful scale at which you should be resolving communities. This is the opportunity, this is the kind of analysis you now have the opportunity to perform because the cluster Leiden function lets you just so easily change that resolution parameter in here. So I strongly encourage you to be making use of these tools. Before closing out this first part of my lecture, I want to go back and point out quickly some other packages that I think you should know about, that we haven't had a chance to talk about yet in today's lecture, and that maybe we'll have to come back again in a future year and add additional lectures about some of these newer packages. The new block models package is a wonderful addition to the packages that you can download from CRAN. To my understanding, before this package was recently made available, we had lost the opportunity to do stochastic block model estimation at all inside of CRAN installable R packages. The old package that was available had many years ago was no longer CRAN compliant, and so I highly recommend if you're interested in these kinds of this alternative way of thinking about community detection through stochastic block models, you really want to check out this package. If stochastic block models are of particular interest to you, you should also, I very strongly encourage you to go beyond R and also look at Python. GraphTool is a just absolutely phenomenal package that is really appears to be the most efficient computationally powerful tool for estimating stochastic block models and for doing a lot of other really interesting statistical analyses of networks. So I highly recommend it to you. We also today haven't had any opportunity within the time of this notebook to talk about multi-layer networks. This has all been just about, I have a network and I want to analyze that network. There's a new multi-net package which promises to do some really wonderful things for including community detection, but also other interesting analyses of multi-layer networks. And so if you're interested in multi-layer networks, I would steer you towards multi-net. Among the many things that multi-net includes is a multi-layer graph extension of the modularity quality function. So the idea here is that if I don't just have one network, but I have a bunch of coupled networks that might represent a network that changes over time, or a multiplex network, or networks of networks that are coupled together. And if I have notions of a network and interlayer connections that are connecting together different networks, then basically modularity, there's a principled derivation of an extension of modularity to multi-layer networks that we did a number of years ago that basically ends up amounting, after a lot of math in the derivation, that the right thing to do is within each layer, do whatever you were doing before. So if it's an undirected layer, then it's again this Ki, Kj, the S's are just indicating which layer you're in. I should note, if you don't have an undirected layer, but you have a bipartite layer or a directed layer or a signed layer, then use the appropriate null model within that layer, and then add together contributions every time that you took a node that's connected to another node in another layer. So for instance, I'm myself in my network of friends, but I'm also myself in my network of colleagues at work. And if my the appearance of me in this multiplex network as in the friends layer gets clustered together in the same community as my work colleagues layer, then that's an interlayer identity arc that we're going to add a contribution to multi-layer modularity. That contribution over here is often written with a prefactor that scales everything by omega. So the reason I bring this up right now is that we've just spent this entire lecture working through the R notebook to show how we need to sweep over gamma. Now, we've got a different gamma potentially inside of every layer. Even if we just say all those gammas are going to be the same, we now also have to sweep over this omega. If I multiply this factor by omega, then as I make omega very large, what that means is that every interlayer edge, every notion of identity between a node and that same actor in another layer there's a higher pressure to keep them in the same community. If I make omega very small, then instead, willy-nilly, I can change those affiliations if the intralayer data indicates that they should be in different networks. And so now I have the gamma I have to sweep and the omega I have to sweep. And this is what we're going to talk about some of the theory about in the second lecture. Some of the code that's available there to do this. There are extensions of Louvain and extensions of Leiden, in particular in Python, that that allow you to do this multi-layer community detection. Again, Multinets lets you do multi-layer community detection. Our Gen Louvain software is a MATLAB contribution. Now what we have, if we look at that roll call similarity data, is we have senators and different senators who appear at different times. So if we stack together all of the different congresses of Senate roll call networks into one big multi-layer representation of a temporal network, then we can cluster appearances of a senator in a Congress by their voting patterns and by whether or not then the interlayer connection is whether or not that senator appears in 2 consecutive Congresses. And you can do this and you can analyze things. And this is a picture from the original multi-layer modularity paper that shows that you can find very rich details in this data. But this is a picture for a single choice of gamma and omega. And you need to pick meaningful parameters of gamma omega. And this is what we're going to focus on in the next part of the lecture. Because if you don't pick meaningful parameters, what you might end up doing is you might end up telling your political science colleague that the Civil War turns out to kind of have been a big deal. So here we have colors indicating the community assignments of senators representing different states at different Congresses. And you can see there's a big split because basically all of the green community disappeared at the start of the Civil War when they all left the Senate and were replaced on the back end of the Civil War by a new community that came out. And that's maybe not the most useful and interesting result to tell your friends in the political science department. So what we're going to do next is we're going to come back and talk about the and beyond part of this lecture. And we're going to talk about what kinds of tools will help us with this parameter selection going forward in the future.